Hello, everyone. So let us continue this lecture on CMOS-based transmitter and receiver design based on inverters. So as we had discussed in the previous lecture, remember that the transmitter and receiver here are going to be inverters, and we are assuming that this link has a length which is much shorter than the shortest wavelength of the transmitted signal, and also the data rate is typically less, and therefore this link has a negligible value of the parasitic inductance, and therefore we can model the link by using an RC network with differential R and C elements connected in cascade, which is driving some load capacitance. The load capacitance being the input impedance, basically the input capacitance to the receiver stage, which could be the PMOS and NMOS capacitors if the receiver was basically another inverter, or it could be some kind of digital logic. So the equivalent circuit model is as shown here. So for example, the input logic could drive this transmitter, which could be a beta inverter. And this beta inverter is basically driving the link, which finally terminates at some load capacitance. So before we continue further, we need to talk about a very important concept called as propagation delay. And to understand this, let us consider the following scenario where there are multiple inverters connected in cascade. So in this situation, you have one inverter, beta 1, connected to a beta 2, beta 3, beta 4 inverter, which is finally terminating, say, at some capacitance C. And let's denote the outputs at each one of these nodes as out 1, out 2, out 3, and so on. So there's a cascade of inverters. And let us assume that the input signal is now transitioning from 0 to 1 with a certain rise time TR. So we can represent this cascade inverter chain by using this equivalent circuit model where you have basically the PMOS and NMOS, which have been sized with respect to the unit inverter by the factor beta. And now what you see is that when the input transitions from 0 to 1, in this first inverter, the output is going to transition from basically from 1 to 0, and then the output 2 is going to transition from 0 to 1, and so on. But because each one of these transitions would basically involve charging and discharging of, so in each case, so in each stage, you see that the actual load that is seen. So imagine you're looking at stage one. Stage one, which is the beta 1 inverter, is basically driving the beta 2 inverter, and therefore looking into the input side of the beta 2 inverter, it sees a load capacitance, which is beta 2 times the gate capacitance of the unit inverter, which we already talked about. And therefore, we see that each one of these stages sees some input capacitance of the next stage, and hence there is some delay in the signal in propagating from one stage to the next, right? So that's what I've written here. So the input gate capacitance of any beta inverter is going to be beta times the gate capacitance of the unit inverter. And similarly, the on resistance of any beta inverter is going to be 1 over beta times the on resistance of the unit inverter. This has already been discussed in the previous part of this lecture. And thus, now we can see how the signal would propagate. So at each stage, say some nth stage which has some beta n, and let's say the beta n is basically trying to pull up the output. So the VDD will be connected through R1 over beta n to the capacitance of the next stage, which would be beta n plus 1 times the gate capacitance of the unit inverter. And thus, if you have this kind of RC, R and C connected in series in this form, the time that it takes for the voltage at this node, at the input node of the next stage, to rise from, say, its original value of 0 to VDD is going to be dependent on the the RC time constant of the circuit path. So you can see here how the voltage grows with time. So the voltage initially at 0 is now going to grow all the way to VDD. And if you use basically solve the circuit, we find that the voltage as a function of time is going to be VDD times 1 minus e power minus t by tau, where tau is the time constant, the RC time constant of this charging process. And the time that it takes basically for the signal to go for the output voltage at basically the output voltage here, which is the input to the next stage, next inverter stage, to go to VDD over 2, called as a propagation delay, is just going to be substituting this V over T as VDD over 2 and simplifying, we would get this propagation delay to be equal to natural log 2 times the time constant tau. The time constant tau just being the RC delay, which is going to be 1 over beta n R on times beta n plus 1 times CG, right? And so, how would that look in the circuit, in the actual in a graphical format? So the input is going to go from 0 to VDD, and let's say the zero point 0.5 VDD occurs at some time as indicated here. The next output, so out 1 is going to transition from 1 to 0, but because of the presence of this on resistance of the beta 1, in this case the beta 1 NMOS, which is discharging the out 1 to 0, as well as the input capacitance of the beta 2 inverter, which is beta 2 times the gate capacitance of the unit inverter. Therefore, we will see that there is a certain propagation delay TP1 in going from the input to out 1. Similarly, there's a certain propagation delay TP2 in going from out 1 to out 2 and so on. And here, the reason why these propagation delays add up is because we are assuming that exactly when the signal transitions 50% VDD is when the inverter is switching from one to the other. So for example, say the inverter was initially pulling low, that is the output was connected to ground through the NMOS, then we assume that the output will be pulled high or the PMOS will be turned on only when the input transition has crossed VDD over 2. Only then we assume that switching happens. So if we do that, the overall propagation delay for this cascaded set of inverters is just going to be the sum of the propagation delays of each stage, where the propagation delay of each stage, say for example, the first stage is just going to be natural logarithm of 2, which is 0.69, times the on resistance of the PMOS or the NMOS, PMOS or the NMOS of that particular stage, which is going to be 1 over beta 1 times R on, times the input gate capacitance of the next stage, which in this case is going to be beta 2 times CG. And thus the overall delay at the output is going to be the sum of the individual propagation delays of each one of these stages. So now let us again look at this cascaded inverter chain that we have. So there's beta 1, beta 2 up to beta n. So the total delay is going to be the sum of the delays of the individual stages. So it's just going to be the sum from I goes from 1 to n of basically the propagation delay, which is the natural logarithm of 2, 0.69, times the time constant of every stage of the ith stage, summed over I goes from 1 to n. And therefore, this is just going to be equal to sum over I goes from 1 to the n minus 1 stage of the delay plus the final delay, which is because of the charging of the output load capacitance here through the on resistance of the nth stage. So it's going to be 0.69 1 over beta n R on times the load capacitance C. So this is going to be the overall delay in signal transmission from the input all the way to the final load capacitance C. And thus the overall propagation delay can be written down in this expanded expression. So it's going to be the sum over all stages up to the n minus 1 stage of 0.69 times the on resistance of the ith stage times the input gate capacitance of the next stage, which is the I plus 1 stage. Plus, this is basically the boundary term, which is going to be the delay of the final stage, which is 0.69 times the on resistance of the nth stage times the load capacitance of the output. So now let us go back to the link case. So now we have looked at the concept of a propagation delay. We have also looked at the concept of how when we have a cascaded inverter chain, we can calculate the overall delay, a propagation delay of the signal in going from the input all the way to the output of the chain. And why do we really care about propagation delay? We know from before that as the propagation delay increases, the signal is basically broadening and delay is occurring in the signal. And this basically leads to a lot of timing issues at the receiver and also can lead to basically signal integrity issues. So ultimately, the design of a good link just means we need to minimize the propagation delay TP. And we will see later that this design actually involves minimizing the propagation delay TP subject to some constraints being, for example, the area occupied by the transmitter or receiver on the chip or the power consumed by the transmitter and receiver. So as we already written before, circuit-wise, this is the link. And we already have now a model for the propagation delay of the transmitter or the receiver. Let us now talk about what about the propagation delay of the link itself. Usually, if you look at this link and we determine the output, so we have basically this link, and there's an input to the link and there's an output to the link, and the link itself is modeled as some differential RC elements. Usually, in order to solve this, you have to solve the circuit, basically the lumped element KVL and KCL at each stage. And then if you do that, just similar to the transmission line model, you'll get some kind of a wave equation which has to be solved to get the output voltage and output current. But however, in our assumption, so for the purposes of our link design, when we assume the low data rates through the link, as well as a relatively short link compared to the shortest wavelength of the transmitted signal, then we can use an approximation to calculate what is the propagation delay of the signal from the input to the output, which is called as the so-called Elmore delay. And the way you calculate this Elmore delay is, imagine this is basically our link. So imagine now it's being pulled high. So there's a VDD here. So this is this VDD, and then there's the on resistance of the PMOS, which is going to be 1 over beta times the on resistance of the unit inverter. And then there's this whole RC link, and finally you have this node at the output of the receiver. And what we will now do is we will find a way to calculate what is the delay of this distributed RC link using an approximation called as the Elmore delay. So how do we actually derive the Elmore delay? So remember this link that was described earlier. The way we calculate the Elmore delay is we basically add the individual time so remember that the propagation delay is just 0.69, it's just natural log of 2 times the time constant of the RC network if there's a single R and C. But here there are multiple stages of R and C. So the way that the Elmore delay is calculated is that you basically add multiple time constants together to create an overall equivalent time constant. And then you multiply 0.69 by this equivalent time constant, which is called as the Elmore delay, to get the overall propagation delay. So the Elmore delay tau d is basically defined in this network as basically the time constant in going all the way to this node, and then the time constant going all the way to this node, ignoring this capacitance, and so on. So it's going to be the RC delay, basically the RC of this link, then the RC of this link, ignoring this capacitance, and so on. So it's going to be R1 over beta plus this resistance, which is going to be RL over N, if you're dividing into N elements, times this capacitance, which is CL over N, plus then it's going to be this resistance plus this resistance plus this resistance times CL over N, and so on, all the way till going at the end, where it's going to be basically R1 over beta plus adding all these resistances that are there, which is N times RL over N, times the load capacitance C load, plus the basically the capacitance CL over N that is found basically at this, because here this capacitance is in parallel with another capacitance here. So it's going to be C load plus the CL over N. So if you now take this equation and then we solve this tau d, uh, we basically simplify this and solve this tau d. And then if you follow the math here, and we take the limit that n tends to infinity, then this so-called Elmore delay of this distributed RC model just ends up being this expression. So there's going to be one term, which is the boundary term, which depends on R1 over beta, times times this C being the capacitance, basically the value of capacitance per unit length times the length, plus the load capacitance, plus RC load times the length of the link, plus RC over 2 times the square of the length of the link, which is RC over 2 L square. And hence the overall propagation delay, that is the overall delay, is going to be, as we already know, 0.69 times the time constant, and the time constant here being the Elmore delay, and therefore the overall propagation delay is going to be 0.69 times this expression. To actually understand the origins of how this Elmore delay approximation really approximates the time delay of an RC link in this fashion is beyond the scope of this lecture. So now we basically have this case where we have this input digital logic, which is connected to this beta inverter. And then you have this whole RC link, which is finally driving a load capacitance. And the overall link propagation delay in going from VDD all the way to the output node is just going to be this TP, which is 0.69 times the Elmore delay of the link. So that is what I have basically written here. So now we have everything that we need. We have the concept of propagation delay of the inverter, a single inverter, as well as the propagation delay of a cascade of inverters, as well as the propagation delay of the RC link itself. So now we are, as I mentioned earlier, signal integrity and the design of the transmitter and receiver for these short low data rate links ultimately comes down to how you can reduce or minimize the propagation delay subject to some constraints. So now we are in a good stage to try to design basically this transmitter and receiver in order to drive these short low data rate links. So now a little intuitive understanding of why we need why sometimes using a single inverter is not a good idea, but we need a cascade of inverters. So imagine for designing the full communication link, which is basically the short low data rate link, it turns out that a cascaded inverter chain is often more efficient than a single large inverter. Now, it's very easy to intuitively understand why this is the case. We already know. So imagine now you have the link, which is driving some load capacitance, which is the input capacitance of the receiver side. And so we already know this propagation delay of the link itself is going to be basically this Elmore delay, as shown here. And now what happens is imagine you use a single large beta inverter to drive this link. As we already know, the beta inverter basically has an on resistance, which is the on resistance of the unit inverter over beta. But the input capacitance of a beta inverter is beta times the input capacitance of a unit inverter. So such a large inverter, although it will speed up the data transmission through the link, it will slow down the previous input logic. Similarly, if you use a small inverter of beta, in this case, what happens is this would basically slow down the data transmission to the link because of the larger on resistance of this beta inverter. However, it would relatively speed up the behavior of the input logic because it adds a very small input capacitance beta times CG. So in case one, it slows down the input logic and speeds up the transmission. In case two, it speeds up the in case one, in case one speeds up the transmission and slows down input logic. In case two, it slows down the data transmission but speeds up the input logic. So now we need to find the best of both worlds because in order to optimize the overall propagation to the delay to the link, we need to minimize both the link delay as well as not add more delay at the input logic. And therefore, it turns out that using a cascaded inverter chain, we get the best of both worlds because now we can have a gradual change in the inverter size so that we have now a large inverter at the output side, which is going to speed up the link, but you have a small inverter at the input side, so you don't add more capacitive delay to the input logic. So this is why a cascaded inverter is basically going to be the most optimal solution to designing this kind of a digital CMOS-based link versus using a single large inverter or a small inverter. So that's what is described here. You can pause and read over what is mentioned in the three cases. So now let us look at how to mathematically design the transmitter side of the link, and then we look at how to design the overall link, including the transmitter and receiver. So the transmitter side, there's going to be some input digital logic, which is as shown here, which is going to go through some Rin, and Rin is just the Thevenin equivalent resistance of the input digital logic. And this Rn is basically going to drive a bunch of cascaded inverters, beta 1, beta 2, beta 3, all the way up to beta n. And the beta n inverter is going to be connected to the link. And the link has a length of L, which is finally going to drive the load capacitance C load. So remember that basically this has multiple delay elements in it. One is there's the propagation delays of the cascade inverter chain, which can be added, as was discussed earlier. And then there's the Elmore delay in the link itself. And so the overall propagation delay is now going to be essentially the overall propagation delay is going to be the RC delay of the input. So because there's this Rin, And then there is some input gate capacitance here, which is going to be beta 1 times CG. So it's going to be 0.69 R in times beta 1 CG. Plus, this is basically the overall delay offered by the cascaded inverter chain. As you can notice here, this is summed from j equals 1, which is the first stage, all the way to the n minus 1 stage. And it's just 0.69 times the on resistance of the jth stage times the input capacitance of the j plus 1 stage. And then this is the Elmore delay of the entire link, which is transmitting the data to the load capacitance C load. And now we have this overall propagation delay, and we can treat this as a cost function. And we essentially need to minimize this, and therefore we just take the partial derivative of the propagation delay with respect to the design parameters, which in this case are the beta j's for j goes from 1 to n. So the derivative of the propagation delay with respect to beta j for j goes from 1 to n must all be equal to 0. And if you actually do this, take this differential and equate it to 0 and go through the math of doing this, what we get is that we get one basically one differential equation over here corresponding to the input boundary term. This is the output boundary term. And then we have one which is the middle, basically the middle region, which is the cascaded inverters. And then if we basically go through the mathematics of doing this, basically this optimization, what we will find is that the optimal solution is found when for the jth inverter, the square of the size of the jth inverter is equal to the product of the sizes of the inverter succeeding it as well as the inverter preceding it. So if we size these inverters in this form, then the delay would be minimized. And similarly, you also have the boundary terms, and the boundary terms basically if you work out the boundary terms, we find that for the first stage, the square of the size of the first stage must be equal to the on resistance of the unit capacitor, the on resistance of the unit inverter over the input resistance of the basically the digital logic input times the size of the second stage of the cascaded inverter chain. And similarly, you also get a boundary term for the basically the nth inverter. And for the nth inverter, you get an expression like this, which says that the square of the size of the nth inverter is going to be related to the size of the n minus 1th inverter, but by this ratio of the total capacitance of the link plus load capacitance over the gate capacitance of the unit inverter. So, of course, there's a lot of tedious math that is involved here. I would definitely suggest that you look more closely at this expression and try to basically optimize this by taking derivatives with respect to the design parameters and setting them equal to 0 yourself. And then trying to work out that these are the basically the equations, the design equations for designing this cascaded inverter chain. So therefore, putting everything together, we basically have these design equations for the jth stage, the first stage, as well as the nth stage. So looking back at our basically our original model for our transmitter, which is driving the link, if we basically say we wanted to design a 10-stage chain, then n is equal to 10. And if we let beta 1, which is the input, the first input inverter, to be as small as possible, and therefore it's a unit inverter, then you can just use these equations to solve what should be the size of the second inverter, the third inverter, and so on in an iterative fashion. And so in this way, you can now design the entire cascaded inverter chain, which has an optimal propagation delay. So this is basically a good example, a good model of how you would go about designing and optimizing this overall digital transmission link to minimize the propagation delay, which is a key metric in this very simplified version of a short low data rate link. So obviously you can make this analysis much more complicated. So in this case, I've given an example where I have designed both the transmitter side as well as the receiver side. So therefore, you can have in the transmitter side, you have the input digital logic with an input resistance, and you can have the basically n stages of this basically the beta 1, beta 2, and so on, cascaded inverter chain. And similarly, the receiver side, you can have a different cascade inverter chain, theta 1, theta 2, up to theta m. And obviously the thetas and betas are not the same, and n and m are not the same, which is finally driving the load capacitor, which is the input capacitor of the essentially the output digital logic in chip 2. And therefore now we can do the same thing that we have already discussed. We can write the overall propagation delay. Obviously, first there is a boundary term because of the RC delay of the input with respect to the input capacitance of the beta 1 stage, plus this is the delay of the cascaded chain, plus the Elmore delay of the link, plus the delay offered by the receiver side cascaded inverter chain, and finally the delay offered by the final mth stage theta m discharging basically charging or discharging the load capacitor C, which is basically C out, right? So this is actually C out. It's written as C here. It's a mistake. It's C out, which is the output capacitance of the digital logic and chip 2. So not only do we need, in most cases, not only would we have to optimize for the propagation delay, we also need to optimize we need to minimize the propagation delay subject to some constraints. So for example, one of the constraints could be the overall area of the transmitter and receiver. So as we already know, the size of the inverter is going to be essentially proportional to the gate capacitance, because the larger the gate capacitance of the inverter, it means the wider the inverter is, and therefore it means that the larger the size of the inverter is. So therefore, if say A is the area of a unit symmetric inverter, then the size of a beta inverter is just going to be beta times A. And therefore, the overall area of the transmitter plus receiver here is just going to be beta 1A plus beta 2A and so on up to beta NA plus the sizes of the theta inverters, which are the receiver side inverters. And we can also have another constraint, which is the total power consumed, which, as you know, in digital logic, the power is CV square F. And we already know that C, the capacitance of any beta inverter is just going to be beta times the gate capacitance of the unit inverter. And therefore, you can basically write the overall power in this way, that there's going to be a CV square F term for each one of these beta inverters that are switching at the transmitter side, plus the link power loss, plus the basically CV square F delay in the theta inverters on the receiver side, plus the final CV square power loss in charging and discharging the load capacitance C out. And now we can define a cost function to be equal to the propagation delay plus Lagrange multiplier lambda 1 times A plus lambda 2 times P. And now we can use the methods of Lagrange multipliers in order to minimize or optimize the propagation delay subject to the constraints of minimizing the area as well as minimizing the overall power dissipation. So obviously you see that the analytic design of the overall link, including the transmitter and receiver, can get quite complicated mathematically. And typically these things are not done this way, but they are rather done automatically through in modern digital design by computers themselves. So how would we mathematically represent this? If you use Lagrange multipliers, you have to take the partial derivative of this cost function with respect to all the design variables. Beta j has to be 0, theta j has to be 0, as well as in order to perform the Lagrange multiplier method of optimization, the partial derivative of the cost function with respect to the Lagrange multipliers must also be 0. So we get a whole set of equations from which we can get the design equations. And from the design equations and making some assumptions, such as the fact that the beta 1 inverter has to be, we start with a unit inverter, then we can design all the values, we can get all the values of beta 1 to beta n and theta 1 to theta m, which completes the design of our entire transmitter and receiver link. So now, what if the link was actually longer or it was even higher data rates? So if the link was actually longer, then we no longer can ignore the parasitic inductance which is present in the link. And therefore, we have to go for a full RLGC model, which is as shown here. But if you have a full RLGC model, what happens is we no longer can use a very simple cascaded inverter to drive such a link, because a link tends to have a wave that is propagating in it, and this wave can have various sort of wave-dependent phenomena such as reflections and so on. And therefore, things such as matching, the impedance matching at the source side, impedance matching at the receiver side become more important. And the presence of these inductances also add more noise and distortion to the signal that is received at the receiver side, which, as you can see here, it's much more distorted. And therefore, it can lead to much more bit errors as well as signal quality reductions. And therefore, just using a simple cascaded inverter chain would give you a significant bit error. And therefore, you may have to use a much more complicated transmitter and receiver with the use of basically matching as well as equalization, error corrections, and so on. So if the link, in summary, if the link was longer, basically than the shortest wavelength of the transmitted signal, or if the link had a very high data rate, then we have to use the full transmission line model, and the design of the transmitter and receiver becomes much more complicated, and we can no longer use cascaded inverter chain driver, and we have to end up actually designing something called as a SerDes, which is outside of the scope of this lecture. So now let us look at some basic concepts of when a SerDes is needed and when a SerDes is not needed. So imagine a conventional package. So in a conventional package, there's chip one, which is at the package level could be basically could be attached to some package, such as it, for example, it could be flip chip bonded using C4 bumps to a laminate, which then could be assembled on the PCB using BGAs and so on. And similarly, you now have package one and package two connected on the PCB. In this case, because of the physical limitations of making links on the PCB, the number of links on the PCB are obviously going to be limited compared to the number of links that actually come out from the chip itself, which is the chip pads. And since there is this mismatch in the number of links on the PCB versus the number of links that come out of the chip, you have to basically serialize the data. So imagine that the chip one was generating data at the rate of G bits per second. So these G bits per second now has to be further divided into M channels. And therefore, what ends up happening is this G bits per second is now divided among M channels. So the data rate per channel is now going to be essentially G over M bits per second per channel. And hence, since the channels M are often very limited compared to the number of very limited compared to the number of compared to the number of links that actually need to come out of the chip, the data rate per channel is actually quite high. And therefore, in a typical PCB, this approximation that we use of the RC delay model no longer applies, and we have to use a full transmission line model. And for a typical package, we do require the design of SerDes. So in this case, for example, there will be a serializer at basically chip one side that serializes all the input data. And then the serial data is sent at a much higher data rate and a much higher voltage through this link. And then finally, it is deserialized at chip 2. And obviously, because this is done at a higher data rate, we have to consider things like matching, equalization, and so on. However, if we consider the case 2, which is actually, which will be described later in the course, called the silicon interconnect fabric, which is an advanced packaging technique wherein we no longer have the PCB, the package, and the laminate, but rather the chip in die form is directly attached to some interconnect fabric where the interconnects can be made using back end of line processing at very fine interconnect pitches. Then you can basically significantly increase the number of links N, or the number of channels. And also, because these chips can now be placed very close to each other, the link length also reduces. In this situation, as the number of links N is now much higher, since the total data generated by chip 1 is G bits per second, the data per link is now going to be G over N. But because N is a much larger number as compared to the M channels in the PCB case, this data rate per channel is now going to be much lesser. So the combination of a much smaller data rate per channel along with the shorter channel in using this advanced package with multiple parallel links at fine interconnect pitches means that these links can now be modeled using the simple RC delay model or the Elmore model, and therefore we can drive these links just by using a cascaded inverter chain at the transmitter and receiver. So later on in the class, we will discuss how going to advanced package such as silicon interconnect fabric significantly simplifies the communication overhead and simplifies the method of communication, and we can end up just using a cascaded inverter chain to drive the links between two chips. So why have we talked so much about this concept of basically signal delay and signal quality, and why is it important? So this usually comes down to this is of course a very diverse topic, and I'm talking about a very small subset of this topic, which is something called source synchronous timing. So imagine you had two chips, which is chip one and chip two, and chip one has its own logic block which is basically connected to a transmitter, which is sending the data over the link to the receiver and finally outputted to logic block 2. Both of these transmitter and receiver are usually synchronized with a certain clock signal, which is supplied to both the transmitter as well as the receiver in such a way that they are synchronized. And then what we do is we only sample the data, or the data only makes sense when it is sampled either at the rising edge or the falling edge, or both the rising edge and falling edge of the clock. So if the data is only sampled at either the rising or the falling edge, respectively, then it is called as a single data rate. If the data is sampled both at the rising and the falling edge, it is called as a DDR or a dual data rate. So imagine now at the input in here, we send this kind of digital data, a bunch of zeros and ones, with a certain, basically with a certain rise time and fall time. And at the output, we already know that the signal is going to be delayed because of the delay in sending along the link. And also there are going to be signal distortions because of the nature of the link itself. There could be frequency dependent dispersions and other effects, which was discussed actually in the signal integrity class. And therefore now what ends up happening is, say you are basically sampling the data over here. One important constraint is there, which is that when the data is sampled, the data has to be stable for a certain time before the sampling location as well as after the sampling location. And this is necessary for the digital logic to actually work. And the minimum time before the transition where the data has to be stable is called as the setup time. And the minimum time after where the signal transition occurs is basically called as a hold time. And therefore, if the signal is delayed too much, then what happens is, because you see now, because the signal is delayed, at the sampling period now, the data is no longer stable for the minimum time t setup, and therefore the setup time of the data has been violated. And similarly, you can also have a hold time violation. And if you take a course on digital design, you will understand that the setup and hold time violations basically lead to errors in the processing of data, and therefore they have to be avoided. And this is the real reason why we care so much about minimizing the propagation delay in these links. So, thank you.